Hey everyone, this is Connor with the Engineering Fellows. Right now, I'm here with a video. I'm going to talk about total and stagnation, total/stagnation conditions, total stagnation, the same thing. I have it written right here. What they mean for a flow, how we utilize them. I'm gonna try to keep the math out of it. There's gonna be a little bit of math, but we're gonna try to just have a conversation as much as we can. All right, so let's get into it. So total, stagnation, same thing. These are properties of a flow, right? So when I say properties, I mean that like a flow, if you can imagine is like it's its own unique thing. And every time you're, if you're at a different altitude and a different, if it's air temperature is different density, maybe there's like moisture in the air that's affecting the density, all that kind of stuff. That all, those are all properties of flow, and they come together to like define the flow, right? So these are innate to the flow and constant under specific circumstances, right? And I'm sure you've heard this before, right? There are some of these characteristics that can change given certain circumstances. I won't spoil it. And usually what these conditions are talking about have to do with the enthalpy and entropy in a flow, right? So real quick, let me go over that. So enthalpy, I have a nice little definition right here that maybe I've made up myself, and maybe I didn't. Who knows? Wrote these notes a while ago. So enthalpy I have is a tool for combining / quantifying the internal energy and work done on or by some system, right? And so we have you've probably seen this equation before in your thermodynamics class. This is the internal energy. And then I think this is rho v. I think it should be PV. I think it would make more sense if it was PV. And note that these are, this is specific. Actually, you know what? Don't note that. Not super important for what we're talking about. This is the internal energy, and this right here, PV, is for us on a gas. That's the work done on or by a gas. Specifically, if you have and then you can change from this H. Generally, we talk about like a delta. Changes in enthalpy, right? It kind of talks about the total heat. Wikipedia, or what am I looking at? This is an Oxford definition. Also says this is the total heat content of a system, right? We usually care about changes in those because those tell us, what was acting on the system, how that system was affected in some way. And then we also have entropy, which is this guy right here. I had to take a quick second to go look that up, but I like this definition, the unavailability. I haven't actually seen that before, but the unavailability I think is a really good word for this because it's basically, if you imagine, if there's energy in a system and then there's, friction or something like that, that friction energy, while if you're looking at a system that encloses some smaller system, that heat is still there, but you can't do anything with it, right? It's kind of lost its usefulness, unavailability. So when you maybe heard this before, the big freeze or something, like the increase in entropy of the universe as we spread out and we cool down, there's like less stuff we can do with that energy just because it's in a less useful form, right? So usually when you think entropy, think dissipative effects So as dissipative effects happen, or as you encounter dissipative effects, you increase the entropy of your system. You become less available to do something useful with the thermal energy in that system, right? So given this, let's talk about the big four. We use these a lot. We have T naught, H naught, P naught, and rho naught. And I've written them out. This is the temperature, enthalpy, pressure, and density of a flow, and specifically of that flow slowed to 0 meters per second. And specifically, adiabatically, boop, boop, same thing for this guy, and then isentropically. Right? So adiabatically, for us, means there is no heat transfer. There's no change due to adding heat or losing heat in the system, right? And for us, that generally means no friction, no viscous effects, right? So right, and you might be thinking, oh, that sounds like a dissipative effect. Does that mean the entropy doesn't change as well? And that's not entirely true. An adiabatic process has no complete this thought a little bit. There's no heat transfer, but there are plenty of other ways where you can have dissipative effects that are not encompassed by an adiabatic, a process that is described as adiabatic, right? Isentropic it specifically means that we are not seeing any increase in entropy, right? And so one way we talk about this is so isentropic includes, so if it includes adiabatic, right? If something is isentropic, you're not going to have any heat transfer, because that would indicate that you're changing like the useful, you're losing some usefulness. Heat is moving in or out. You're not able to use that heat anymore. Either you can't, so you can't decrease your entropy, right? You can't go backwards from that. You can't cool. You can't warm a cup of cold coffee in a cold, anyway, you can't gain that energy back naturally, right? So it's adiabatic, and then also reversible. We're going to take a dive on, I think it's IBL. I think we're going to, maybe it's ABL. Either way. And this reversible kind of encompasses all the other ways you could lose that ability to do useful work that is not just the heat loss, right? And so when we think of things that are isentropic, these are things that happen very nicely. It's like conservative forces, stuff like that. You go one way and you can go backwards the other way, and you pretty much gain everything you lost. If you put something on the ground, you pick it back up, you're not doing anything that can't be undone, right? A chemical reaction is something that once it happens, you can't just naturally undo that process, right? And the way we see it a lot, especially now that we're looking at supersonic flow, is in shock waves. So for a shock wave, you have an irreversible process. All right, so across a shock, we have this violent kind of, and we also put out a video with this one on shocks, but we have this violent change where we've abruptly changed the flow in really I'll say it again, violent way, and we can't undo that. It's irreversible. And so that means that shocks are isentropic. So something like P naught and rho naught are not going to be constant along after a shock, right? Because if you're going from one flow and then you basically go through this irreversible process, and you're not keeping that isentropic characteristic between those 2 points on either side of a shock. However, shocks are also adiabatic. Abiadatic. So, while we don't, while we do have an irreversible process, we don't have a process where there's no friction, there's no heat transfer over a shock, right? So that means we can say that T naught and H naught are constant from one side of a shock to another, right? And then fans, I talked about this in the other video. Fans are a very nice, easy process. They're very relaxing. The flow gets to stretch out. It gets a lot more space. Fans are isentropic. All right? If something's isentropic, it is automatically adiabatic, right? So it is both isentropic and adiabatic. And in that case, all of these are constant on either side of a fan. Did I say, I feel like I just said shocks are isentropic. They're not. Fans are isentropic. And these are kind of, these are, so what we talked about just now. So basically said these stagnation conditions, T naught and P naught and H naught, these are characteristics of a flow. And if you shove them through a shock, some of them don't stay constant. You've violently changed the flow too much to ever go back, right? So you end up with a new P naught and new rho naught. However, enthalpy doesn't change, and total temperature does not change, right? Another way to write these, which I actually really like, and I have it written down right here, is you can kind of think of these as a bigger picture of Bernoulli's equation, right? And for Bernoulli's equation, we had, and I don't have it off the top of my head, but it's like cut. Should I go find that? So I have it now. Bernoulli's equation says that if we take, P plus P1 plus 1/2 rho 1 V1 squared equals P2 plus 1/2 P2 V2 squared, rho 2, right, along some streamline where, it's isentropic throughout. Right, that's a very nice characteristic, and it was really comfortable, or it was really nice for us to use in incompressible flow. What we can say is that, similarly, H naught and T naught are constant along streamlines. Steam lines, come on. For adiabatic flow. And similarly, P naught and rho naught are constant for isentropic, good lord, isentropic flow. Make that look a little nicer. Come on now. So this is really nice because then we can set up equations like, you know, h1 plus v1 squared over 2. This is kind of like the total work, equals h2 plus v2 squared over 2 equals h naught. Anywhere along this streamline, you know, not 1, 2, as long as this is adiabatic, right? It's really nice because if there's a shock between, you know, 1 and 2, we're still able to use this relationship. It's really helpful. All right, I think I've said all I wanted to say. And I'm looking at my notes, and there's a lot of other equations that come out of these assumptions that I know you guys are going over in lecture, and there's a lot of them are also listed out, you know, or derived. The isentropic relations over a shock, or sorry, not over a shock, isentropic relations between 2 points in a flow, and then similar relations for, let's see, I've got a few others here. You can do, you know, based on the Mach number, based on, you know, oblique shocks, normal shocks. Definitely have those equations on your crib sheet. Those are super helpful. But with that, I think we're just about done with this video. So thanks for tuning in. Good luck on your exam. And this has been Connor, the Aerospace Engineering Fellows.